Hi, welcome to this work example. In the lecture you were introduced to traveling waves, and traveling waves are waves that do not only vary in time, but also in position. A famous example of the traveling waves are the ocean, and we do not look at all the water of the ocean, but only on the surface, so the surface waves of the ocean. Here we have our expression for our common traveling waves, which is S as a function of x and t, is a times the sinus of k times x minus omega times t plus v. In our situation, a is the amplitude, which is d over 2. Since d is the distance from the top to the bottom, this is twice the amplitude. K is the spatial frequency, and in the lecture I was told that this is 2 pi divided by lambda, where lambda is the wavelength of our wave. Omega is the temporal frequency, and it's 2 pi divided by the period, t. It was given that the time it takes to go up and down is tau, so our total period is 2 tau. Therefore, our temporal frequency is 2 pi divided by 2 tau, which is pi over tau. If we combine all of this, we obtain that our wave equation is capital D divided by 2 times the sinus of 2 pi over lambda times x minus pi over tau times t plus v, where v is just our phase shift. So now we want to measure the depth of the ocean, and we can do this by sending sound signals into the ocean and see when they come back. In the lecture I was told that the speed of the wave is omega divided by k, and it was shown that you can derive that it is 2 pi times f divided by 2 pi divided by lambda, and this is a lambda times f. It was given that the lambda and the f for sound is 75 millimeters and 20 kilohertz, and if we multiply this to each other, we obtain that the speed is 1500 meters per second. Note that these are the values for the sound waves and not for the waves of the ocean, so we have two traveling waves in one situation. The time difference was given to be 120 milliseconds, so if we multiply this with the speed, we obtain that the distance is 180 meters. Note that this is the distance the sound has traveled, and it's not the actual depth of the ocean. Since the sound takes some time to go back and forward, we can have a small phase shift because of this time delay. Now, what is this phase shift? We can assume our x is constant, so we do not move, so x is x0. And we have t1 when we send the signal, and t2 when we measure the signal. At t is t1, we can have that our wave is a function of x0, and t1 is capital D over 2 times the sinus of 2 pi over lambda times x0 minus pi over 2 times t1 plus v. And we can do the same for t is t2. We obtain a similar equation, but now t2 instead of t1. And we can write t2 as something else. It's t1 plus the difference of t2 and t1. And this may seem odd or strange, but this will become clear why I do this. If we now fill in this expression for t2, we can work out the brackets and see that both expressions are very similar. The only difference is the time difference component, and this causes the phase shift. This means that our absolute phase shift is pi over tau times t2 minus t1. So what is the actual depth of our ocean? Well, small d is the measured distance, and this is twice the depth of the ocean plus the height of the boat at t is 1 plus the height of the boat at t equals t2. Well, we can rewrite it to obtain that the depth of the ocean is small d divided by 2 minus the height of the boat at t equals t1 divided by 2 minus the height of the boat at t equals t2 divided by 2. We can fill in now our expression for our wave, and the first wave moment is capital D over 4 times sinus of 2 pi over lambda times x0 minus pi over tau times t1 plus v. And if we fill in our second wave equation, we have an additional minus d over 4 times the sinus of 2 pi over lambda times x0 minus pi over tau times t2 plus v. This equation is horrible, and we can try if we can simplify it. Well, the assumption that we're given was t1 is 0 and v is pi over 2. If we fill this in, we can see that our both signs have a phase shift of pi over 2. Well, this is equal to a cosine, since a cosine is always pi over 2 radians ahead of the sine. And this equation is already much better, but we can do better. The last assumption we could make was that the boat was at maximum height at x is x0 and t is t1. This means that x0 should be such that the first cosine is maximum, thus a multiple of 2 pi. This means that x0 should be lambda times n, such that if we multiply them, we get a multiple of 2 pi. If we substitute x0 into our equation, we obtain the following, and we can now work out the lambdas. For the first cosine, this is 2n times pi, where n is just any integer. This is always 1. And for the second cosine, we have 2 times n times pi minus pi over tau times t2. And if you add 2 pi with cosine, it doesn't change. So our expression becomes the following. It's small d over 2 minus capital D over 4 minus capital D over 4 times the cosine of minus pi over tau times t2. And for cosines, negative values and positive values are both the same, so we can forget about a negative sign. This is our final expression for the depth, which is small d over 2 minus capital D over 4 minus capital D over 4 times the cosine of pi over tau times t2. So to summarize what we have done, we've looked at a situation where we want to measure the depth of the ocean, and we are on a traveling wave of the ocean itself. These traveling waves can be described by the equation s of x comma t is the capital D over 2 times the sinus of 2 pi over lambda times x minus pi over tau times t plus v. When we want to measure the depth, we have to send sound waves and measure them back. And this causes a time shift of a phase delay, which is pi over tau times t2 minus t1. And with this, we could finally determine the depth of the ocean, which is small d over 2 minus d over 4 minus capital D over 4 times cosine of pi over tau times t2. And this concludes this work example. Thank you for watching and good luck with your exercises.